the main author, David Seidler from Zurich, Switzerland. So the paper talks mainly about string processing, and they mention it's an important type of query because the huge amount of data collected from the web. For example, you have tweets from Twitter, millions of posts from Facebook, articles from Wikipedia, you name it. And they also mention that these are the operations these are the string operations, for example, contains, which checks if a word is presented in text, like if a substring is presented in a text, and regex p, like if a regex presented in the text. And these are in order of increasing complexity. We also mentioned that some operations might benefit from indexes. So for example, suffix trees, n-grams, and inverted indexes. But they also mentioned that indexes do bring the good side, but they have the bad sides, which is a substantial amount of space. They must be updated during insertion, and sometimes they need to be rebuilt periodically. They also argue that databases are not really efficient with string operations. So to illustrate this point, they run the following experiment. The time to answer one query on 2.5 million strings. They compare MongoDB running 10 threads and DPX, which is a commercial row star, which they don't say the name, but according to Diego, it's SQL Server.
Probably, yeah.
Yeah. Okay.
If it's systems code, it might be Oracle.
Nah, but the guy was working at Microsoft, so.
He did the internship there.
Yeah.
He mentioned the paper.
But it's DPX, we don't know. And they do want to illustrate that the more complex the operation is, the longer it will take, but they all have pretty much the same string to check. One solution that they propose is to make use of accelerators like GPUs, FPGAs using the PCI Express, or many core architectures like XeonPi, but they mention that these accelerators have some shortcomings. For the XeonPi, the data needs to be reformed so that you can use SIMD execution. Yeah. And for, well, apparently for all of them, the data needs to be partitioned. It's in the main memory, but you also need to send it to the accelerator. So one possible solution is those hybrid architectures that have reconfigurable hardware embedded as a normal processor. So you have IBM Power 8 plus CAPI that uses PCI Express to communicate between the accelerator and the CPU. And you have Intel Xeon plus FPGA, which uses the QPI bus to communicate. And they say that both of them have cache coherent memory access. So this was the introduction, and these are the contributions. Personally, I think that the biggest contribution is the second, where they present the hardware-based regular expression engine that can be reconfigured during runtime. So this was the introduction. Now let's go to the background. So they do mention FPGA. So this is more or less how a basic FPGA looks like logically. So it has programmable interconnects, programmable logic blocks, and programmable I/O blocks. And they also mention it behaves similar to application-specific integrated circuits. And they also mention the architecture they're using, which is Intel Xeon plus FPGA. As I mentioned before, the FPGA has cache coherent memory access, and they measured a throughput of 6.5 gigabytes per second on a read-intensive workload, and on a read and write, it's 3 gigabytes per second. And they mentioned that the low bandwidth is because on the FPGA, the QPI endpoint runs at 200 megahertz, that's why it's so low. They also mentioned that the system on top of this architecture is Ubuntu 14.04 with a special kernel made by Intel to communicate with the FPGA, which they call Accelerator Abstraction Layer. This kernel is responsible for doing all the memory allocations. All the memory pages have 2 megabytes granularity page size, and they are contiguously pinned in physical memory because apparently the FPGA cannot handle page faults. And because the kernel has some kind of limitation until when they wrote the paper, the size of the shared memory could be only 4 gigabytes. but they said it would not be the case on newer versions. So now the system overview. This is more or less how their system looks like. They do use MongoDB because of the UDFs, which can process on entire columns instead of one tuple at a time. They modify MongoDB to use the shared memory only. And they also have this Centaur, which in the presentation is called Centaur, but in the paper is called HAL, which is Hardware Operational Abstraction Layer. I don't know why they changed it. And this is just an interface with the kernel. So imagine the query comes. So first the query comes to MongoDB, it queries with a regular expression. Then MongoDB redirects it to the UDF with the regex string and the column. Then the UDF converts the regular expression into a configuration vector, allocates the memory for the result path, for the result column, and calls Centaur to create a new job. Then on the FPGA, the job distributor select one of the regex engines, one that's idle, and sends the job there. The regex engine executes and then returns the result to the UDF. Now let's just look how a regex engine is inside. So it looks more or less like this. It has a string reader which will read blocks of strings instead of only one. And then it will deliver in a round-robin order to the input FIFOs. Then the PU are the processing units, which are really the regex engine. And finally, you have the output collector, which just makes sure everything's in order. So the regex engine, which is the interesting part of their work. So they do mention that to solve a regex, you can do it by using automatas. I don't know if you can do with other way. I know automatas. And you have two flavors. You have the non-deterministic version, which I'll explain here. And the non-deterministic version, you can have multiple states active at the same time. And you also have the deterministic version, which you can have only one stage active at a time, but it's much bigger. Also, in software, on CPU, you cannot execute the non-deterministic version efficiently because you need to check each stage. And when you do that on the FPGA, you can check all of them at once using real parallelism instead of one at a time. So just as an example of how the NFA would work. So we have the regex, we have the NFA that would solve it, and we have the input AECC, so we want to consume A. We start on starting state, S0, so we consume and go to S1. Now we want to consume the input E. We remain on S1 because of the asterisk. Now we want to consume C, so we go to 2 states, we continue on S1 and we go to S2, and the automata divides into 2. And now here we have a match, but we continue consuming. So now we consume the last C, which will have the same thing will happen, and that automata will divide into 2, and we have 2 matches. You select which one you prefer. Now how their system works. So this is before compilation time. This is all inside the FPGA, but let me see. This is how the engine looks like, but during compilation time, you're going to say, I want 4 nodes, I want 4 states, and for example, here selected 4, and all these 4 states are fully connected inside the FPGA. I don't know how they do it, but it's physically with wires and things like that. And you also have the tokens, which are the alphabet of the regex, which are connected to the states, but not to each other. So this is how the reconfiguration works. So here we have the states. We selected 4 and 4 tokens. We have the same regex as before, and we have the same NFA, just to illustrate. So the first thing is to extract the tokens, A, B, and C, and we put on the tokens slots in the FPGA. The next thing is you determine the state transitions. So S1 remains in S1 and goes to S4. And I know this doesn't look quite the same, but apparently from what I could understand from their paper, they don't really need this final state here, so they have one state less than how you would draw a regular automata. But they don't explain how this translates to this. They just say, here, this is how it's done for this input, this regex. And that's fine, including the example of the paper is wrong. So, yeah. And then we decide what inputs trigger which states. So inputs A and B trigger state S1, input C trigger state S4. So let's see how it would work in practice. So we have the engine and we have the NFA. We have the same input as before. We start on stage S1 and we want to consume A. So the engine consumes A and activates S1 again and S4. The NFA just goes to S2. Now we want to consume E. They don't explain exactly what happened when you don't have the token here, so I'm just guessing nothing. They don't explain. And the NFA just remains on S2. Now we want to consume C. C activates S4, and on the NFA, it will divide again. So when it activates S4, it records a match, and the NFA just continues as it was before. Now we want to consume the last C. And again, the engine will record a match, and the NFA will split. And that's how it works. Now for their experiments. They have two versions of MongoDB, an unmodified version 11.21.19, where they enable multi-threaded execution. And they also have a modified version where they, with the adaptations, to run their UDF using shared memory. And this one, they disable multi-thread execution. According to them, it introduces overhead when using with the UDF. You are the engineers, I don't know. And they also compare against the commercial Rollstar TBX. These are the 4 queries they run. So you have a very simple select, a very simple like query plus query 1, and 3 somewhat complex regex queries. They also have a table with ID and a varchar of size 64 bytes. And the varchar is always something with a name, street, number, city, and area code, like this, concatenated using the pipe character. And query selectivity is usually 20% unless they state otherwise. So the first experiment they provide is the response time breakdown. On this one, they use a small subset of data, only 10,000 tuples. And on the x-axis, you have the queries. On the y-axis, you have the time in milliseconds. And they just wanted to show that the hull or the centaur part, the UDF and the configure generation takes a very small time, and that independent of the query, the UDF with the FPGA takes the same time. The next experiment, the response time of each query when they vary the number of records. So on the x-axis is the number of records, on the y-axis is the response time, and this dotted line is the FPGA ideal, which they say is the FPGA without the bandwidth limitation. And interesting thing is that on using the FPGA, all the queries have the exact same response time or very near. So all the 4 lines for the FPGA are on top of each other. And for simple queries, MongoDB is faster after 2.5 million records of the table on the table. And for a complex query, MongoDB is a little bit slower. And when compared to the DBX, they are always faster. For
Can you briefly go back to the previous one?
Yeah.
Okay, so they're both logarithmic scale, I suppose.
Yes.
Yeah.
Yes.
Well, the small. I just got triggered because the small ticks are missing on the y-axis in the second graph. Okay.
But I find it strange because it's such a short time. They don't mention if they execute a workload or for only one query anyway. And then they have the throughput. They also want to measure, so you have the number of clients sending requests and the queries per second. And they mentioned that for query 1, the FPGA is memory bound, so it has smaller bandwidth compared to the CPU. That's why it has smaller throughput when compared to MongoDB. But for complex queries, the FPGA is 5 to 10 times faster, to 15 times faster. And when compared to DBX, it's even better. And DBX has this linear increase because it assigns 1 query per thread. That's what they mentioned. They also wanted to run TPCH, but TPCH doesn't really have a lot of queries with string operations, so they select query 13. They say that due to the limited memory size, they had to put the scale factor to 0.1. I don't know what that means exactly, but it's probably very small.
100 megabytes.
Yeah.
Of entire TPCH in CSV.
Okay.
It's not a lot.
And they also compared case sensitive and case insensitive, and they mentioned that the case insensitive makes MongoDB takes twice as long, but it doesn't matter on the FPGA. This is probably because of a trick they put there, but I couldn't understand what they did. They do mention it, but I did not understand what they did. And finally, they talk about hybrid execution, which is when the regex doesn't fit inside the FPGA. And what they mentioned as a solution for that is to divide the regex on where it's possible. So they send all this part here to the FPGA, and this is executed on software. And this is the experiment they run. Table with 2.5 million tuples. They vary the selectivity between 0 and 1. And they measure the throughput, and they mentioned that using the UDF with the FPGA, it's roughly 13 times faster at most.
Sorry, can you go back one?
This.
Yeah, but how did you manage to get response time of like 10 seconds on scale factor 0.1?
That's a bit strange, right?
They had like sub-second times for a million of records with the simple expressions, and here they have like 10 seconds.
Yeah, maybe it's supposed to be milliseconds.
It's their plot, right?
And maybe
Yeah.
the plot is just wrong.
Yeah.
It's
Yeah.
probably milliseconds instead of
Probably
seconds.
milliseconds.
Yeah.
Sounds right.
Even with ADB cannot do this, even single-threaded.
Yeah.
Okay, the plot's there, so
Yeah.
just collected from paper.
Yeah, sure.
It's nasty.
Yeah.
That's it.
Thank you.
Thank you.